All right, here we go. This is going to be me simply going over the review sheet for compaction class. So here we are. Number one, the LSRL and its equation have been added to the scatter plot. Use the information to answer the following questions. So here is the equation for the LSRL. That is apparently the LSRL. So we're going to just answer some of the questions. First off, what type of association does this scatter plot have? Well, it looks linear, looks negative, it's strong, I would say. So let's call it a strong, negative, and linear. Are there any outliers? Nope. No outliers. I don't see anything that's way off. It says one of the points on the scatter plot lies at 13.1. Don't worry if you can actually finding 13.1 on there. We're just going to find the residual for it. So what is its residual? Remember, the residual is found by taking the actual data minus the predicted to end up with the residual. So let's see what we have here. So we are going to take 13, we're going to plug it in here to find what the predicted value is. So this is going to be y equals negative 1/6 times 13 plus 5. So it'll give us negative 13 over 6, which is negative 2 and 1/6 plus 5. So add that together and you will get 2 and 5/6 for our, excuse me, that's our predicted value. So our actual value was 1. So we have 1 minus 2 and 5/6, which will give us a negative 1 and 5/6 value. So that is our residual, is negative 1 and 5/6. So we'll put that back over here. There we go. All right, next one. If you were to plot the points 1, negative 2, and negative 1, 4, and connect them with a straight line, is the point negative 38, 114 on this line? Explain how you know. So you can explain or just demonstrate how you know on this one. And the way we're going to do this is we're going to first find the equation of the line. So to find the equation of the line, we need to first find the slope. So remember, slope is found by figuring out the change in y. So from negative 2 to 4, that goes up 6 over the change in x. So it was up 6. And then that goes down 2. So our slope is negative 3. So as we write the equation of this line, it's going to be y equals negative 3x plus something. How do we figure out what the y-intercept is? Just take one of those points, plug the x in, and see what you need to get the y out. So if I were to take negative 1 and put it in here, negative 3 times negative 1 is positive 3. So positive 3 plus something has got to come out to 4. Well, 3 plus 1 is 4. That means my y-intercept is 1. So my equation is y equals negative 3x plus 1. Now, how do I tell if the point negative 38, 114 is on the line? Well, I put the negative 38 in for x and see if it gives me 114 out for y. So let's do that. So we're going to get y equals negative 3 times negative 38 plus 1 and see what do we get. Do we get 114? Well, negative times a negative is positive. 3 times 30 is 90. And then 3 times 8 is 24. So that adds up to 114. Add 1 to that, we get 115, which is not 114. So no, it's not on the line. Okay. Let's see here. Number 3, below's table showing the average price of a gallon of unleaded premium gas on Labor Day for a period of 7 years. Analyze this data. Use the parameters given and answer the following prompts. So write the equation of the LSRL. So how are we going to do that? Well, we've got the information down here. Remember, this goes in for M, and then this goes in for B. So to write the equation, we just got to put in that slope and y-intercept. Let's round to like the thousandths place. So the equation is going to be y equals 0.064 x, and then it's going to be a negative y-intercept, which doesn't make a ton of sense, but we wouldn't be going back a couple thousand years to see what the price of unleaded gas was. So negative 126.127. All right, describe the shape and the strength of the scatter plot. Well, shape meaning like, is it linear or not? And yes, it is. And how strong of a linear association, is it positive or negative? So all we need for that is R right there. That's the rating scale, remember, for how strongly this fits a linear relationship. And it's 0.94, which means it's a very strong positive linear association because the correlation coefficient is 0.9408. Okay, so this would be strong, positive, and linear. All right. Make a statement about the linear relationship between the two variables. So what are the two variables? The variables are year and price for unleaded premium gas. And so we would use R squared to help us make that statement. So the R squared here is 0.8851. So we're going to say about 88.5%. 0.5% of the data can be described using a linear relationship between year and gas prices. So that's all we're going to say. All right, so there we go. Finally, write the equations of the upper and lower boundary lines. In order to do this, we need to find the greatest residual, absolute value residual. So as I'm looking over here, you don't care if it's negative or positive, whichever one's the greatest. And so this looks like this is it right here. So we're gonna use 0.094. We're gonna add that to the y-intercept and subtract it from the y-intercept. So let's go over here. So I need to take that negative 126 and I am going to add, so this negative, let's see here, negative 126.127. I'm going to add the 0.094 to it. So let me write that down. So plus, and I'm going to subtract 0.094 from it. So the equation, so the upper boundary is going to be y equals 0.064x, and that'll be negative 1 minus 126.033. Okay, and then the lower boundary is going to have the same slope, obviously. It's going to be y equals 0.064x minus, and then that gives us, oh, I did it the wrong way. Hold on. I got to do this one more time here. So, sorry, doing this all in one take. So I'm not going to go back and edit, hopefully. Because negatives 126.221. There you go. So there's the equation of the upper and lower boundaries. Okay, so here, just kind of skipped ahead just so you didn't have to watch me write all of this stuff down. But I've scaled my graph accordingly. So down below, this is going to be the height in centimeters down here. And the shoe length in centimeters is going to be going this way. It's the y-axis. You can see I've put the points in there roughly. This doesn't have to be perfect, just got to be close. And then we can use it to help us answer the questions. For A, it says draw a possible trend line. So if I'm going to draw a trend line that goes through that, again, you're just going to want to try to make sure that the line goes through the middle of the data, get approximately half the points above, half below. I don't know how good that one is. I could maybe adjust it just a little bit here. So maybe that would be a little bit closer. Regardless though, we need to now use this to help us to answer the rest of this. So for B, it says, is the relationship between height and shoe size roughly proportional? Remember, proportional relationship is linear and it goes through 0, 0. Now, obviously, you would think that if their height is 0, shoe length is going to be 0, so that would make sense. But if we were to extend this line here, it's not looking like it's going to go through 0, 0. So I would say that no, this relationship is not proportional because the line is not going to go through 0, 0. Remember, trend lines don't always fit every little aspect of real life, and they kind of sometimes are only related to the data that you're talking about. So the parameters, you don't necessarily want to go any farther left or too far right from where the data that you collected is. So I would say no. In this case, how can I tell? The line does not appear as though it will go through 0, 0. Okay, so Tapita adds her height and shoe length to the graph. Does this new data point follow the trend? Well, let's see where her point is. So 165 and 17. So 165 is about here, and then 17, if we go up, is right about there. What do you think? Does that seem to fit the data? I would say no, it looks like an outlier. And if you want to explain a little bit more, you could say it doesn't fit the linear relationship, or it doesn't seem like it'll go on the line or fit in that line with that data. All right, moving on. Below is a table showing average heights in centimeters for girls ages 7 through 15. And there's the data. Okay, Leroy calculated the LSRL for this data would be right there with a slope of 5.22, y-intercept of 85.5, and he feels that this is a pretty good model for his data. He might feel pretty too. I don't know about that. Let's see. According to Leroy's LSRL, what is the residual for a 12-year-old? Well, what we got to do is we've got to find the predicted and then subtract that from the actual. So it's going to be 150 minus something to get so this is going to be the predicted here. Again, we got the actual there, and this will give us the residual here. So let's put 12 in for X there and see what we get. So get out your calculator, and we got 5.22 times 12. And then we're going to add on 85.5 to that, and it will give us 148.14. So 148.14. And then if we subtract that from 150, we will get, oops, I just cleared it out of my calculator. We got 1.86, and I probably should have just done that in my head, but oh well. 1.86. And it's going to be positive because the predicted was less than the actual. So this is a positive residual. So 1.86, and it looks like I got a typo. I was supposed to do what's the residual for the 15-year-old on this one. I'll try and fix this for your document. So I wanted it to be for a 15-year-old, so I found a typo. That's good. Okay, continuing where we left off. So typo here was that this is for a 15-year-old that we wanted. So that means that the actual for the 15-year-old was 158. We need to now figure out what the predicted was. So if we put 15 into X here, let's see what we get. So let's see, that would be 5.22 times 15, and then add on to that 85.5, and we get 163.8. So if we're going to take away 163.8, we're going to get a negative residual in this case. It's going to be a negative 5.8. So a negative 5.8 residual. Okay. So now, moving on. Leroy thinks he can use the LSRL to estimate the height in centimeters of his 27-year-old cousin Matilda. What a name. What do you think? Be clear and complete. Well, obviously, you stop growing somewhere in your teens, usually. And if we're going to use this linear model to project out to someone who's 27 years old, it's not going to make any sense because they'd be a giant. Just think if you used it to project out for someone who's 100 years old, they would just be, 100 times 5, that would be, 500 centimeters plus another 85 would be huge. So, no. People stop growing. Cannot spell. I suck. Okay. Humans stop growing usually in their teen years. So, this wouldn't make sense for a 27-year-old.
Alondra Olivo to the office, please. Alondra Olivo to the office.
Okay, so cruising along here. This one, we need to do a little bit of work. So we're going to distribute the 2x here. So that'll give us 2x squared, which makes this a quadratic. Plus 2x minus 2 equals x plus 3. So we're now going to maybe subtract x on both sides. And we're looking at 2x squared.